Good morning, everybody. Happy Wednesday. So, I guess for today, I'm going to just resume from last time's lecture. So, we did sort of begin talking about binary trees, mostly just sort of what's the structure of binary tree and sort of how to kind of construct it, not really in a loop or iterative fashion, but just kind of step by step, just to get an idea of the structure of binary trees. And that's basically about it. So I guess we'll resume from that. So I'm going to begin a screen share. And let's go ahead and just go into this topic. Alrighty, so here we are. So basically, as a recap, well, a binary tree can be expressed in this type of fashion. So we're mostly going to use this picture to represent a binary tree. But in reality, we can think of it as these kind of boxes. We have these two pointers for every single node. So each node will have three sort of fields, some data field, and then we'll have these two pointers, one that points to a left child and one that points to a right child. That's basically about it. So very similar structure to a linked list. It's a little bit more on kind of maybe more of an augmented linked list if you think about it. So anyway, so we can see a struct here for binary tree nodes. Every single circle in the structure is going to be a bin tree node, and it contains some data field and a pointer to the left and right child. So for this binary tree right there, well, let's say for this node 7, well, its right child contains a node 4, and left child will be null in this case. So we'll have an arrow there. So obviously, in the more sort of this kind of more lower level picture, it would have a null for its left pointer, but we just don't really draw. We just sort of show nothing here, which implies there's no child there. Okay, so now that we kind of have an idea of what a binary tree really is, we want to go over methods of being able to operate on them. So one simple method is just, well, being able to traverse a binary tree is kind of, what we want to at least do. If we can traverse a binary tree, then we can do all kinds of operations on a binary tree. Let's go over binary tree traversals. So let's just um, line here and continue with our notes. So binary tree traversals. So we have several, and we'll go over the more common ones in class. So we have preorder, traversal, and postorder. Those are two we will definitely cover in class either today or next week, Monday, depending on how far I get on all these. Then we have inorder, and then we have level order. So basically, these traversals right here, all of these three are going to be recursive. So recursion, our favorite, topic in CS. Um, so basically for binary trees, you have to use recursion to traverse it. Now, of course, you could have a loop instead, but if you have a loop with binary trees, you're going to sort of emulate recursion with a loop. So in a sense, it's either way, it's going to be the same idea. It has to be recursive somewhat in order to traverse a binary tree. And level order, this one's going to be, I guess, not recursive is, I guess, the technical term for this. Not recursive. Now, these two, pre and post order, these two right there, can be applied on any k-ary tree, which really means that these traversals can be applied. So pre and post order can be applied on a tree. So you can have a tree with 3 children per node, which would not be a binary tree. It would be a 3-ary tree, I suppose. A 4 sort of child, so every node has 4 children. It can be applied to any sort of tree structure, even on graphs as well, which a graph is kind of like a more of an advanced tree, which will cover graph theory content later in the semester. But these two traversals can be applied on any type of sort of tree, whereas in order is really specific, so mostly only for binary trees. It's really more for binary tree operations. So we'll kind of, sort of mention how in order works, and really there's only one spot where really actually only is usable, to be honest. So pre and post order are sort of more generic traversals, which can be applied to any tree and also to any graphs. And we won't cover level order right now, but we will cover level order type traversal later on when we go over graph theory. There is a traversal, which is a level order for graph theory, which is similar to level order on any kind of tree. But we'll first go over pre and post order. I'll just sort of give an honorable mention to in order. And then once we have to actually use in order at some point, then we'll address that at that point. But for now, let's go ahead and discuss pre and post order traversals in today's class or possibly next week's Monday's class. So first, before we actually write any kind of code on traversing a binary tree, we want to first, of course, define this binary tree data structure recursively. Let's go ahead and first do that. So let's go over the recursive definition of a binary tree. So to define this structure recursively, we have to, of course, have a base case and a general case because it's a recursive definition, so it follows that recursion model. So obviously, a binary tree, so an empty binary tree is in fact a binary tree. This will, of course, be our base case in our definition of binary trees. So empty tree is a tree, base case. Now for our general case, well, it's going to be the following. Well, it's going to be a binary tree node whose left and right child pointers point to a, well, you could say it points to a node, and that would be correct, but we want to define this recursively, so it's going to point to a binary tree. So I'll sort of underline this, green underline this. So there's your recursion. So every node, its left and right pointer points to a binary tree. And what's a binary tree? Well, it's either empty or it's a node whose left and right children pointers point to another binary tree, which could also be empty or another node. So you can see this as a definition that never ends until we finally hit an empty binary tree. So the idea with this definition, so let me scroll up to this binary tree example just to take a look. So the idea is that, well, we have a root pointer in this binary tree. And the idea is that each and every single node, so I'll circle these as we go. So this is going to be obviously a root of a binary tree, but this node right there is also going to be a root of its own binary tree. So every single node in this structure is really a root of its own smaller binary tree. This is also a root of its own binary tree. And even this node, it's also a root of its own binary tree, because the left and right children pointers both point to an empty binary tree, so this node 1 is also a binary tree. So each node is a root of its own smaller binary tree. That's really the definition of binary tree. That's what it's really saying, essentially. It's just saying that every node is its own smaller binary tree, or root of its own smaller binary tree. So that's really the idea when we have this definition. So now that we have this definition set up, now writing the recursive code to traverse it is actually not really too, not exactly really too strange now, or at least we have the illusion of not being too strange now. So let's go ahead and first start with the code needed to traverse. So using a preorder traversal of a binary tree. So I'm going to have the function defined up here. So void preorder, and it will have a parameter bin tree node star r. So r is going to be a root of a binary tree, or other words, r is going to be a pointer that points to some node in our existing binary tree. And we're going to have the following. We're going to first say, well, if r is null, then we're not going to do anything. We're done. So if r equals null, return. Now, of course, I could actually write this code by say if r does not equal null, then do actual work. But I wanted to have these two cases kind of separated so it's easier to visualize it from this definition and this code. So I want to just make it like this. So if r is null, return. Else, or I guess I can just have no else here because if it's true, it returns so that none of the code below this if statement even executes. If r does in fact equal null, returns, and that function will stop running. So there's no need to have an else case. So I'm going to have, I guess, cout r arrow item. So item will be that field, that data field of a binary tree node, and L. Now I'm going to box this in. I'm going to try to use, let's see if I can do this. Make a nice sort of straight box over here, see if it works. Oh, okay, that worked out pretty nice. So basically, this portion of our code, well, we could do more than just simply output the item in that node. But I'm going to sort of just only output nodes for right now. But if we wanted to, we could do other types of work on this binary tree, which we'll cover examples next week that goes over other types of stuff we can do with a binary tree. But for right now, though, this part here in red is sort of the pre-order work that's done on this node. So you can, of course, do other things, which we will cover that, but for now we'll just output. So I'm just going to box this in, meaning that we could do other things instead. We could have more lines of code and do a lot of operations on this node that R is pointing to. But anyway, that's that. So we first output. So we're just going to go ahead and output all the nodes in our binary tree. And afterwards, we're going to call preorder, pass an R arrow left, and then preorder R arrow right. And then we'll have the optional return statement at the end, I guess, just to be, I guess, official about this. And that's it. We can zoom out so we can see the entire code on one frame. So there it is. This code, of course, will magically just output the entire binary tree. So all we're doing is the following. So kind of in high-level view of this code, we're first outputting sort of the item field of the node R, and then this part of the code is going to magically output all of R's left subtree nodes gets all outputted, and then we're going to output all of R's right subtree nodes. The first output R, then R's left subtree, then R's right subtree, and that's it, we're done. So that's how this works. But we'll, of course, trace this out so we'll actually make sense of all this. So let's go ahead and write the int main portion just to see how this will get called in our program. And then I'll draw a binary tree to the right of this so we can actually trace this code on this on example binary tree. So let's go ahead and write our int main below. So we'll create a bin tree node pointer. This will be our root pointer. Now, let's assume we wrote some code, we called some functions or whatnot, and we just constructed a binary tree magically. We just created some binary tree. So root is going to be a root pointer that points to that topmost node of an existing binary tree. So we wrote some code that constructs a binary tree. So we're going to now call preorder and pass the root pointer as a parameter. So root is going to be the actual parameter, and r initially, when it gets to be called a function, r is that parameter that gets created when the function is called, and that r parameter will in fact point to that root node. Then I'll just return 0 here, and then we'll have an example binary tree, and then try to trace out recursion, see how hopefully we can get a better understanding of recursion now. Instead of thinking about it as magic, maybe this will help us understand recursion a little better. But let's find out. So I'm going to zoom out and show the entire code here. And I'll have a binary tree example. So let's go ahead and draw a binary tree out. So let's suppose that this root pointer points to the following binary tree. So I'll just create some example binary tree. This is a completely arbitrary tree I'm creating right now. So I think this is going to be okay. So there we are. So root will point to this top node. So let's assume that in main we called some functions and we constructed this binary tree using the example method from last time. We can just one by one allocate a node and assign to left and right pointers, and we just create a binary tree. So I'm going to go ahead and put some numbers here. So we'll make this a binary tree of integers. So of course, a binary tree can be templated where we can have each node contain, integer or string or char, or double, or even more of a complex type. Even there's no limit for what we can store into a binary tree, but we'll use integers for right now. Let's do this. Then I'll have 8, 6, 1, I guess 5. There we go. So we have a binary tree example right there. And I'll have the output portion, I'll put this over here at the bottom. The output generated by the following code above. All right. So we first go ahead and call preorder from main. We're passing root into the function. So r is going to in fact point to that node, right? Because we're passing in root initially, so that our parameter is going to contain the same address as root. So it's pointing to that same node as root is pointing to. So let's go ahead and run this function. So let's go ahead and run this line by line. So if r equals null, well, r is not equal to null. So we're going to skip the return statement. So the next statement to be executed now is going to be cout r arrow item. We're going to output the item field of that node that r points to, which is going to definitely output 10, because 10 is going to be the value stored in that node. So we output 10. All right, well, it wasn't too bad. And now, after we do that, we're going to run this line of code. Preorder r arrow left. Okay, so what happens now is this function that we're currently on is going to pause, and it's going to, of course, call preorder and pass in, so r points to node 10. It'll pass in this node's left address. So it's going to pass in this node, the address of that node, into a new function call. So what's going to happen now is when I create a function, when I call preorder, it spawns a new function, and it will spawn its own r parameter. And for this new function call, r is going to point to that node 7. Because in the function call before, we called preorder and passed in 10, this node's left address in. So we're passing the address of 7. That node 7's address is passed into the function. So we have these two r's right there, but they're two separate r's and two separate function instances. They're local parameters. So these two r's are not related to each other. We just had to create a new r because when we call a function, every time we call preorder, a new r is going to be created. So the function above, well, it's sort of halting right there. It's stuck on that line. And meanwhile, we just call preorder r left. So you have to run this entire function call all over again on this new instance. So R points to 7, and we call preorder on it. So let's run the exact same code all over again on this node. Okay, so we have this R parameter created, and R does not point to null. Obviously, it points at node 7. So if statement at the very top will get skipped over, and we simply output R arrow item, which in this case outputs 7, because R points at node that contains 7. So we output 7 next. And after we do that, well, we have to call preorder R arrow left. So once again, this function is going to again stall, and it has to create a new instance. So right now, we're going to call preorder again, and we're passing in R arrow left. So essentially, we're passing in the address of that node is passed into a new function call. So in a new function call instance, this R parameter is going to point to that node 3 because we passed in that address into a new function call. So it's going to spawn a new function, and it's going to have a separate R parameter. And for this R parameter, it will point to that node 3. The previous R's are still exist, but they're in different function scopes. So each R, they're not really related to each other. Not really, in a sense. They're, well, if you want to look at it as a family tree, we can't think of it like that. But for now, they're just 3 separate R's in their own function call instances. So we have to run this exact same code all over again on this node. So, okay, fine, let's run this. So we check if R equals null. It does not equal R null, sorry. And then we're going to basically output the item field, which is going to be 3 in this case, since the R node, this R pointer points to a node that contains 3 for its item field. So we output 3. And now, once again, we have to call preorder within this function body and pass in R's left address. So right now we see here that 3, that node has no children. So right now it's going to go ahead and pass in null into this function. So we're going to call preorder and pass in null. So this instance, R is going to be, I'm just going to go ahead and just, I guess I'll write the whole thing null out just because. So we passed in null this time because, well, 3's left pointer contains null. We're passing in null this time. Let's run this code on this new function instance. This time, however, R equals null. So it returns immediately. We're done. So with recursion, we have these functions on our system stack. So these functions are all stacked up basically, and a topmost function call is this one. That's our topmost function call. To return, like we did right there, we go back to the last function call, which happens to be the function called preorder, where R was pointing to a node that contains 3. So what happened was we were last stuck on that line. So we returned back from that function call, so we have to now resume, because recursion, remember, it remembers where it last left off. So it's going to resume from where it last left off. So it's going to now call preorder and pass an R arrow right. So for this node, well, R arrow right in this case will again be null because this is a leaf node. So we call preorder once again, and we pass in a null pointer again because 3's right child is null. So we call preorder once again by passing in null, and we see here that, well, R is null, so return back immediately. So we go back to the previous function call, which once again, it's a function call where we had preorder called, and R happened to point to node 3. This was the most recent function call we were currently on. So we last left off on that line, because recursion remembers magically where we last left off, which it should, because otherwise, if it didn't remember where we last left off, recursion couldn't be possible. So after we return back, we left off on this line, the next line of code is simply return. So now we're done with that function call. So now we have to go back to the previous function call, which happens to be this function call where we call a preorder and R pointed to the node that contains 7. you go back to the previous one. So really, in layman's terms, you go back to the parent because that's going to be always the most recent function call when doing binary tree traversals. So go back to the previous function call where r point is 7, and we were stuck on that line. We remembered we last left off on that line, so we're going to now continue from that line, which is now we're going to have to call, again, preorder, but this time we're going to pass in the right address for this node. Okay, so we're going to again spawn a new function call, and for this function call, r is going to point to that node. Because we're passing in the previous function level, we're passing in the right address in, so r will be that node. And now we have to run the same code all over again. Very repetitive, but this is kind of how we should, try to visualize because we're going to be running code later on involving, so for assignment 5, it'll be binary trees, and it'll be some type of a form of pre and post order, except you have to do more than just see out, but you will be doing something like this, so it's hopefully this is making sense. So anyway, we now have r point to this node 11, and we have to run this exact function all over again. So r equals null is not true, so we skip this if statement right there. And we're going to go ahead and run this next code, which is simply cout r item, or cout 11 in this case. That's what the node contains that r points to. Fine. That's output 11. And then we go back up and we're going to say, well, after we output item, now we have to go ahead and call preorder r left. All right, well, we have to again, we call the function preorder, we have to spawn a function, and we're passing the left address. So for 11, the left address contains that node too. So we have to go ahead and call preorder and pass in this address into this function. And this r parameter will contain that address that contains 2. All right, well, we have to run this code all over again on this new node. We check it. R equals null is not true because r definitely points to an actual node. So we skip the return statement and we simply cout our item, which couts 2. And then afterwards, we're going to now call preorder on this node, pass in left pointer. Left pointer is going to be null in this case because, well, this is a leaf node. So it's going to be, we're passing in null. We're calling preorder and passing null in, so r in this function instance, r will be null. So in this function call, the very first if statement we have will be true because r does equal null, so return. We go back to the previous function call. The previous function call was where r pointed to the node that contains 2, and we last left off on that line because Recursive remembers exactly where we last left off. We last left off right there, so now we have to resume from this part, which is going to be, well, we got to call preorder again and pass in this node's right pointer in. Alrighty, so this node is a leaf node, obviously, so the right pointer will, of course, be another null. So after that, when we call preorder again, pass in r right, we spawn a new function called instance. We're going to resume this, we're going to call this function, and in this function call, well, r equals null, so that first if statement is true, return back immediately. Go back to the previous function and call, where we had r pointing to node 2, and we last left off on that line. So we have to resume from that part, which is going to be now, well, return, which means this function now is done, and we go back to the previous function call, which will be where we last called preorder, where r pointed to the node that contains 11, and we last left off on this line. We called preorder r left. So we have to now resume from where we last left off, which is now called preorder and pass in r right. Okay, so this node has a null pointer for its right side. There's no right child here, so we're going to again pass in null and call preorder by passing null into r. And obviously, once again, it's going to be null, so return back immediately. And we go back to the previous function call. So last function call once again, it's going to be where r points to that node 11. And we last left off on that line because we did call preorder r right for this function call instance. So of course, with recursion, we're going to resume from that line of code, which is simply, well, return. That's the last line of code there, which will end this function. And we go back to the previous function, which will be this function call, where R pointed to that node 7. And we last left off on that line because we just called preorder R right for that instance. And we return back, so we last left off on that line. The next line of code is simply return. So return back up to the previous function call once again. So now we go back to the very beginning where we had R pointing to root initially. And for this function call instance, we left off on that line. We did call preorder R left for that node. So now we have to resume from where this function last left off, which is simply call preorder R right, which means you're going to, again, spawn new function call, and we're going to pass in this node's right address, which means we're going to spawn a function, create a new R parameter, and this R parameter will point to that node that contains 8. And run the exact same thing all over again. Very repetitive, but that's sort of the only way we can really traverse through a binary tree. I guess I'll finish the example off. I'll try to go a little bit quicker, so maybe it's getting a little bit boring, but hopefully if it is boring, that means it makes sense, which is good. We want to make sure this does sort of make sense. So anyway, we call preorder, and R points that node it contains 8, so it's not going to be null. So we're going to skip the return statement and just simply see out our item, which means see out that node that contains 8. So I'll put the 8. And then once again, we have to go ahead and call preorder R arrow left. And obviously, if there's node 8, there is no left child, so we're going to again pass in null into a new function call instance. So R will be null, so it returns immediately because we hit that first base case, return back to the previous function call, which happens to be this function call where R pointed to that node. So we last left off on that line in this function call, so you have to now resume and call this function, preorder R right. So we spawn a new function call, it creates a new R parameter, and this R parameter will now point to this node because we passed in R arrow right, that address of the right node, into a new function call. So this R will point at node 6. We have to run this function all over again on this new node, this new instance. So R equals null is not going to be true because R points node that contains 6. So we're going to skip that first return statement, and we're going to see out our item, which will see out that node 6. And then we're going to go ahead and call preorder R left. That's the next line of code to execute in this function. So we're going to pass in the left address, which is this node 1, so left address of 6. And run this same code again, so I'll go a little quicker here. So R does not equal to null. So we see out 1. That's the first thing we do. I'll wrap it up a little quicker since I think we see a pattern here. I mean, it's a morning 8:30 a.m. class, so definitely putting us asleep, I think. I mean, if I wasn't talking like this, I would be probably falling asleep actually too on this. So anyway, after this, we call preorder R left, which will be null. It's a null pointer. Returns back up to the previous function call. Then we call preorder R right. It's null. Return back to the previous function call. So for us to know that R points to 1, we last left off on this line, and we return back to the previous function call, back up to node 6. So returning means you go back up to the parent node, basically, is how we can think about this. So once again, we hit this, we go back up to the previous node, we last left off on that line again, so we resume and now call preorder R right, which will go ahead and call preorder and pass in that node 5 into new function call instance. Again, R is not null, so we're going to output the value 5 to the screen. And now, of course, what's going to happen is we're going to call preorder once, which will pass a null pointer because 5 is a leaf node. We'll pass in null, return back immediately. Then it will call preorder R right, which will again pass in null. It's kind of hard to fit this here, but I'll try. Returns back immediately again. So for at node 5, we call preorder R left, we call preorder R right, So now we're done with this function call. We go back to the previous function call, which that function call we had post preorder r pointing to 6. We last left off on that preorder r right. So after this, we resume, which is now we're going to return. Go back to the previous function call once again. We go back to this function call, and we last left off on preorder r right, so we have to resume from that spot, which is simply return. Done with that. Go back to the previous function call, where we had r point to this node. We last left off on that line because recursion remembers where we last left off. And then we're going to return. This next line code return. This function is done as well. Then int main, return back to int main. And int main returns as well. And there's no more functions left on our system stack, which means our program is now done. And that's going to be our output for preorder for the following binary tree. So, all right, so basically, to traverse a binary tree, all we have to do, so in a simple preorder fashion, so we can look at this as well once again. So we first output 10, and then we outputted 10's all of the left subtree. So notice we output 10 first, then we output 7, 3, 11, 2. Then we output 8, 6, 1, 5. So we kind of have that pattern. And then for 7, we output 7 first, then 7's left subtree, then 7's right subtree. But the best way of thinking about this is, for preorder, we just keep going left as far as possible until we can't go further left. Then we back up, and then we try to go right. And again, we go as far left as possible, and so forth. So there's a very defined sort of pattern in which we're moving. Always go as far left as possible, return back, try the other direction, and also same pattern, go left as possible, return back. So it's this very very systematic sort of method. But that's really how we traverse a binary tree recursively. So any questions on this right now? Hopefully it does make sense. So I guess we'll go over the other traversal, I suppose. Why not? So this is preorder. Now let's go over post-order traversal. And then we'll go over, more interesting examples. I mean, I think outputting is kind of boring, but this gives a nice sort of idea for how we can traverse a binary tree. I'm going to go ahead and copy this tree. I'm going to reuse this again for other example. Through other traversal types, see if I can actually successfully copy this. One of the benefits of using OneNote over plain whiteboarding class. Awesome, so looks like that should be good. So now let's go over post order. Yeah, okay, we can think of it like that. It's the binary tree traversal of hello world. And of course, we have to have hello world because what type of a CS class or what type of a new topic in CS would not have a hello world somewhere there? I mean, that's an actual unofficial, unwritten rule of computer science. Every new topic, you must have a hello world portion before we actually do other topics. I can't agree anymore with that. That's exactly correct. So let's go over next the other hello world method. So I'll try to go a little bit quicker here if I can. At least I'll start off slow at the beginning, then I'll just kind of speed this up as we go. So let's go ahead and now write the code here for post-order traversal. So very similar to pre-order, but I guess different. So again, we're going to have our R pointer. And again, we're going to have our if statement that check for an empty tree. So if R equals null, then let's get out of this function. So just simply return. So I could have actually, okay, so just to go back to the post order code, I could have actually said if R not equal to null, then execute these 3 lines of code. I could have done that instead. But I want to separate the base case from the general case just so it's a bit easier to kind of absorb all this. But we could have written it like that. That would have been just as good. But I'll keep the structure like that over here as well. So for post order, well, it's not much different really. We're going to go ahead and do the following now. We call post order R left, then call post order. All right, and then of course have our hello world. See out our item. And then I'll go ahead and I'll box this in. Once again, we could do more than just simply output, but we'll just go ahead and focus on, let's try this again, see if it comes out a little better. So once again, we could do more than just outing the node, but we'll just keep it like that for right now, just to go over a simple example involving binary trees. But that's really it. So the idea here for post-order traversal, so we can see the entire code. The idea for post-order traversal is that we sort of output on the way up the tree. So for preorder, we always would output and then we would traverse. Here we're moving through our tree on the way back. As we're going backwards, we're going up the tree, we're outputting before we leave each function call. So we're outputting in reverse essentially here. So let's go ahead and once again, let's write our main just to get an idea of how this function gets called. And then we'll go ahead and copy and paste that tree and run post order on this example. Let's see how far we get. So I'm going to try to go into other examples today, but I want to first just go over the very basics, just to get an idea of tree traversals, then we can do other more interesting stuff. So we'll have, once again, our bin tree node pointer. This will be our root pointer. Then we'll write some code which will basically construct a binary tree. And then we'll go ahead and just like before, we call post order. And we pass in this root pointer as an argument. And then we return 0, which will end int main. Also, return 0 is important for code grade as well, or else your program will be marked wrong. So return 0 is important, mostly for code grade, I suppose. Or maybe for, I guess there is some reason why, but we'll just keep it simple and just say that's for code grade, really. So anyway, there's going to be our main, which we'll call post order. And this code gets called right there. I'm going to try to copy and paste the tree right there. So it looks like it did sort of copy it correctly. I'm going to erase all of these guys. Takes a little while, but definitely faster than redrawing this entire tree, I think. So that's the positives of using OneNote. All right, erase all that. All righty. So there's our tree. So the same example like we did before, except now we're going to do post order. And I'll put the output portion right over here, as always. All right. So you first call a function. We're passing in root into the function. So of course, R is going to point to the root, and then we're going to begin this long, tedious process again. So right now, R equals null is not true because R points to a node. So we're going to go ahead and run this function right away. That's the next line of code that happens. So we call post order. We spawn a function call once again. We pass in the left pointer in. So we call post order again. And we're going to have this R gets created for this new function called instance. And R points to that node that contains 7. The function above, it's sort of stuck right there. But it's not done. It's still in memory. It's still in the system stack, but it has to wait until its function is done at that level. So right now, we're at this point. So again, we call post order. R is not null. So we have to go ahead and call post order R arrow left, which will just basically, again, spawn the function call. It'll create a new R parameter, and that R parameter will point to that node right there. And then again, R is not equal to null. We skip that return statement up top, and we go ahead and call post order R arrow left, which would just basically pass a null pointer. And this function called instance, R equals null, so again, return immediately because it's a null pointer. Go back to the previous function call, which is where R points to 3, and we last left off on that line, so we have to resume, and now we have to call that function call. Okay, fine. So we're going to have to pass in null because the right side of 3 is in fact null. So we pass in null, return back immediately, we're done. Go back to the previous function call. So the previous function call was where r pointed 3, and we last left off on that line. The next line of code is simply output the item, which will output 3 in this case. That. And then we're done. After this output statement, we escape, return out this function, go back to the previous function call. So the previous function call, r pointed 7, and we last left off on that line. So now we have to go ahead and now call postorder r right, which will spawn a function call, and this function call r will point to that node. And then for this node, we'll run the same code again. R is not null, so we skip that return statement, and we have to call postorder r left, which is going to go ahead and call postorder and pass in that node, the left child of 11. And then for this function call instance, r is not equal to null, so we skip that return statement. We call postorder r left, which will pass a null pointer, returns back immediately. Go back to the previous function call where r points to 2. We last left off on that line. So go to the next line. We continue, which we call postorder r right. And it's going to basically pass another null pointer again because the right side of 2 is again null. It's a leaf node. Return back immediately. And we go back to the previous function call. So the last function call we had, r points to 2, and we're last stuck on that line. So we have to resume from that line and simply output the item, or output 2 in this case. And then, after that, return. We're done with this function after we output. Go back to the previous function call where r points to 11. We did call postorder r left. We last left off on that line. So now we're going to now call postorder r right. All right, so for this node 11, it has no right child, so it's going to pass in a null once again. And it's going to immediately return back because r is null. Hit that base case. Return back to the previous function call. So the last function call we had, r pointed to 11, and we were last stuck on that line, so we're going to resume from that spot, which will be simply output the item, which means output 11. And after that, the function call is done. Return back to the last function call. The last function call was where r pointed to 7. We last left off on that line, so we have to now resume from that spot and output 7, which is the data field in that node that r points to. The output is 7, and then this function call is done. Go back to the previous function call where now r points to 10. We last left off on that line in that function, so now we have to go ahead and call postorder r right. So we're going to create a function called instance, and r will point to that node. Again, r is not null, so you have to go ahead and call postorder r left. So for 8, its left side is a null because it has no children there. Return back immediately. Go back to the previous function call where r pointed to 8. We last left off on that line. Now we have to resume and now execute that line. So call postorder r right. So it creates a new function call instance. And for this function call, r will point to that node. And then what's going to happen is, well, we check r is not null. So we're going to call postorder r left. So we have r pointing to this node now. Again, r is not null. So we have to go ahead and call postorder r left. So it's going to pass in a null pointer because it's a leaf node, returns back. We have to call postorder r right because then we go back to the previous function call. We last left off over there. So now we have to resume and now call postorder r right. And for node 1, the right side will also be null because there's no children there. Return back to the previous function call. Return back to node 1. We last left off on that line. So next line execution will be see out the item because after we called postorder right, we resume from that spot, which means see out the item field. So we're going to see out 1. Ready? And then we're going to return back to the previous function call where r pointing to 6. We last left off on that line. So we have to now resume and now call Postorder on the right side. So we call the function Postorder once again. And for this function instance, r will point to that node. And we have to call that function all over again for that node. R is not null, so we skip that first return statement. Then we call Postorder r left, which will pass in a null, returns back immediately. And then the previous function call where r pointed to 5, we last left off on that line. Now we have to call Postorder r right, which in this case the right side contains a null again because there's no children for this node, returns back immediately. We go back to the previous function and call where r pointed to 5. We last left off on that line, so we have to resume and now run this line, which is simply output node 5, or output the value of that node, which is 5. Like that. And then we're going to return. The next sort of line of code is return. Go back to the previous function call where r point is 6. We were last stuck on that line, so we have to resume from that line, which is simply output the item, which will be outputting 6. And then return. Go back to the last function call, r pointing to node 8, and we last left off on that line because the recursion remembers we last left off. And then we're going to go ahead and now run this line, output the 8. And after that, return back to the last function call, go back to where r pointed to 10. We last left off on that line, so we resume from that spot, output the 10. We're finally done with this example. Thank goodness. And then, after we output the 10, return, go back to main. Main also returns. There's no more functions left in our system stack, and we're now done. And that was the post-order traversal of a binary tree. So we see here in this version, really sort of, it didn't really, so the output was a little different. So we always, as we return, as we keep on calling the function, before we return back up, then we output. So preorder, when we first enter this node, we output first, and then we do everything else. Post order, we first have to output the left side, then the right side, then return, or then output the node. In other words, we always output before we return back to the last function call. So preorder, we first output, then process everything else. Post order, we process everything else first. Before return, we go ahead and output on the way up, on the way back, basically. So we output 3 first, then 2's output, then 11, then 7, because once we process 7's left and right side, we have to return. Before we do that, though, we output the value. So that's really the pattern for how we can sort of see this. So anyway, that's post-order traversal. Any questions on that? So yes, so a system stack that maintains the function calls is limited, but if you have a lot of memory in your system, it will be able to run a lot. But at a certain point, though, if you're out of stack space, then your function, your program will kind of crash. A segmentation fault or a stack overflow will happen. So we have to, if you have a very big tree, then the stack could be very large for each function call. Because here we have a lot of, well, we could potentially have a lot of functions that are being currently called. Now we do pop functions off the stack as we return back up, but potentially you can have a very long path along that left side, which will constantly keep pushing function calls. So of course you can avoid recursion and use a loop-based sort of traversal, but even that you have to push nodes onto a custom stack. So either way, it requires a stack one way or the other. So you have to have a lot of memory potentially if a tree is very large. But we'll assume for right now in these examples that the stack is infinite in size, but limitations for sure exist when traversing because the stack is not endless, unfortunately. You have a lot of memory essentially to do this, yeah. So I'll give an honorary mention to in-order traversal. I'm not going to write the entire code out for this because I don't want to traverse this anymore. I'm sort of sick of traversing this in order, and pre-order stuff. It's really not interesting, but it's important to understand this, so of course. So for in order, I'll just give a honorary mention to this. It basically is the following. We have to first call in order, r left, then we have to process the node that r points to. So again, I can also box this in red as well. Let's be consistent. Hopefully I get this nice and straight box. Looks like it's okay. Okay, looks pretty good. And then we call in order and pass an r right. That's in order traversal. So I guess if you wanted to practice, you could actually trace this out on a binary tree, but I'm not going to really trace this out. That's how in order would work. And we can see here, it's really specific to binary trees because we have exactly two children. If we had an n-ary or k-ary tree, then we could do this in between, but it would kind of make no sense. So really, this only really works on binary trees. And there's actually a reason for why we do this, but we'll go over later on as to what's the purpose of in order. But really, the main traversals is going to be pre and post order. So that's my honorary sort of mention to in order traversal. I'll underline this too, sure. In order traversal. That was quick. Much faster than pre and post order. So now I'm going to go over some examples of doing other things besides just boring pre and post order traversal. So let's first talk about, let's discuss a function. Let's go ahead and write a function that's going to count the leaf nodes in a binary tree. That's a kind of a better application. At least it has some application, I suppose. But let's go over a program that will count the amount of leaf nodes in a binary tree. So I'm going to create a function. I'm going to have return int type. Int count leaves. And we'll have a bin tree node. Actually, okay, you know what? I'm gonna not do this just yet. Sorry, I'm gonna do this afterwards. I guess I forgot. I want to cover this example first. My mistake. So I'm gonna go over an example where I want to try to find an element in a binary tree. Yes, I want to start with that one first. That one is definitely what we're talking about. So bool find. So similar to find an element in a linked list or an array, I want to write a function to find an element in a binary tree. So I'm going to have bin tree node star r, and then I'll have int s, which is going to be our search value, and we'll write the code. So first, of course, we have a few base cases here. So one base case is if r equals null. So that's always, we have to always consider an empty binary tree. So if r equals null, then of course we have to return false. So this implies that we didn't really find this s value. It doesn't mean it's not in the tree, but remember, for a tree structure, we have multiple different paths we can take. So this particular path that we're currently running did not find s. S could be somewhere else. We have to, of course, back up and try a different path. But this path that we're currently taking does not contain the value s. Then, of course, if r is not null, well, let's go ahead and check. If r item equals s, well, that means we found this search value along this path. Return true in this case. So if R is not null, so we had a failed search, or if the item doesn't equal S, let's say R is a node, but doesn't contain S, that means, okay, so far we haven't found S, but we can't really conclude that S is not in this path. So we have to go ahead and keep trying. So I'm going to do the following. I'm going to say, I guess I can probably do this in one line. I'll do it in one. I'll do it the long way, or a short way, sorry. So return find R left S, or find R right S. And now, of course, I could have made two variables that returns the found sort of function, or returns that find function result on the left and right side. This one's a little bit shorter. So of course, in this case, we're going to first search the left side. If it returns true, then we're done. Because remember, this OR operator, we can have this short circuit evaluation occur. Let's say if find R left S equals true, then true or, well, whatever this is, doesn't matter. We're not going to even call this function. So if find R left returns false, then we're going to have to go ahead and try find R right. If it returns false as well, then false or false, return false. If right returns true, then false or true returns true. So we're going to sort of relay these true or false values up the tree. So that's going to be our traversal of find element in a binary tree. Let's go ahead and draw an example binary tree and sort of trace this one out. It's a bit more interesting, I think, than pre and post order because we do other things, I suppose, than just... Oh, it's kind of in the way right there. All right, I'm going to try to shrink this then. Perfect. So now we'll have this example code. Let's go ahead and create a tree. And let's go ahead and write this function that will find an element, or it'll return true if it found it and false if it didn't find the elements. So let's go ahead and create a binary tree here. I could use the same one from last time. Hold on, let me see if I can copy and paste that here. That will be a little faster than trying to draw that entire tree out again. Yeah, this is better. Definitely saves time versus writing the whole thing out again. Okay. This part's a little slow, but I guess it is sort of therapeutic to erase these. I don't know why this feels so therapeutic doing this. I guess, erasing is always, if you have a pencil, you have to erase really hard. This is kind of like a very pleasant and easy to erase, so it does feel therapeutic to do that. So anyway, here we are. So we have our root created. So let's go ahead and just write some code for int main. Let's suppose, once again, we have our bin tree node. Root created, and we have some code that builds up this binary tree. And then I'll create if statement. So I'll go ahead and I'll say if find root, and I guess I'll try 8, I suppose. So find and root and 8. So this will return true because 8 obviously exists in this binary tree structure. So we'll see out found. Then I'll go ahead and I'll create another if statement. I'll call find again from main. I'll say while not find root, and what do we not have in this? I'll try, 12. Let's try 12. 12 is definitely not in this tree. So it should return false. Then we'll see out not found. So we're going to just trace these out just to kind of get a better idea. But if you understand pre and post order traversal, it's actually not too bad to trace this code out. There we are. So you first call find, pass in root and 8. Okay, so I'm going to have the following. I'm going to have R, we'll point over here, and I'll put actually R, and I'll put, I guess, 8 right below. So we kind of remember that 8 is that second parameter we're passing in. So we have to run this code and check. So is R null? It's not. Is the item equal to S? It's not. So you have to go ahead and call find R left. Of course, you have to always do this part first. So what's going to happen is we call find R left. So again, we pass in R and 8. Once again, is R null? It's not. Is the item equal to 8? It's also not the case. So you have to go ahead and call find, pass in R left, and S. So this is sort of, you know, like preorder in a sense. It's kind of like that. So then we go ahead and we check is R equal to null. Is the item equal to S? It's not. So you go ahead and call find R left. So what's going to happen now is at this level, R is going to be null. So return false. So that implies that we did not find 8 along this path. So 8 could still be in our structure, but this path led to a failed search. Okay, so we go back up to the previous function call, where R pointed at 3. We called this function found R left. It returned false. So now we have to go ahead and now try this function, which is going to be find R right. So then, again, we're going to call this function, and right now R is going to be null because this node has no children, so return false immediately. So at this function level, well, we called find R left for this node 3, and we called find R right. Both return false, so false or false, return false up this way. So all we know right now is that node 7, the left side led to a failure. Now maybe 8 is on the right side. We don't know, but we know for right now left side definitely failed. It didn't find 8. Okay, so we have to try the right side because when you go back to the previous function, we always leave off on this every single time. We first call the function. For the first time we enter, we first call that. It returns false. So now we have to call find R right. Because it was false, we will in fact have to run this. If it was a true, then this would short circuit, so which means you wouldn't have to call the second part, but in this case it's false, so we have to. So we go ahead and pass in R here and 8. R is not null. It's not equal to S either, so we're going to have to call the function find, so you have to go ahead and run this part for this function called instance because we first call find R left using the code given right there. And R will point to that 2. And 8 is going to be the search value. Right there we can see that R is not null and the 8 is not equal to 2. So you have to go ahead and call find R left. Put it over here actually, so it's a bit easier, so I'll put it here. You go ahead and pass in null. So in this situation, we hit our base case, returns false. Go back to the last function call, and we had R pointing to node 2, and we're last stuck right here. It returned false. So we have to go ahead and now try find R right next. So for this node 2, the right side is going to be null once again. And 8 is that S value. So R is equal to null. Return false. So at that level where R points to 2, we called find R left and we called find R right. Both returned false, so false or false equals false, returning false up here, indicating that for this function call above where we're at 11, The left side led to a failure. It didn't find 8 there. Okay, fine. So maybe the right side contains 8. Maybe. So in this situation, we have a leaf, so 11 contains no right child. So we go ahead and call find R right, because after we call find R left, we must call find R right. So R will be null. It has to be the 8 value. Again, we have a null case if R equals null, return false, according to our code. Like that. Let's go to the previous function call where R points at node 11. The left side, we called find R left, and we called find R right. Both return false, so return false. I should have actually crossed this off as well as this one, my mistake. So now with the function call above, where R points to 7, we called find R left and we called find R right. Both returned false, so return false back to the root. So the root level, we're stuck right here. We called find R left, it returned false. So we have to go ahead and call find R right, because it's the next sort of step in this code. We first call find R left, then we call find R right. Unless find R left returns true, then it will short circuit and not have to call find R right. But here it returned false, so we have to call R right, which will go ahead and have the case where R will point to this node, and R is not equal to null, but now our item does equal S. Our item contains 8, S is also 8, so we finally found a successful search. So here, return true at this point. And for root level, well, we called find R left, return false. We called find R right, return true. So false or true returns true. So let's say, for example, if let's say at the root level, we're trying to find 3, it would go ahead and call find R left, and would find out S equals 3, it returns true. At a 7 level, it would not call find R right because it already found 3 left sides, so forget about it. Don't call find R right, return true immediately. Up to the root level, at the root level, find R left returns true, so we don't have to call find R right. Return true back immediately. And then main returns true, cout found. Now if you do a find root 12, what would happen now is every single instance we would hit a base case of R equals null. So for every single node, every single function call instance, the find R left and find R right would always return false in both cases. So eventually the root would get return of false because left side would return false, the right side would go through all those steps, and then these falses gets returned back up, and the root level would have a false or false, turn false, and then I guess not false would execute this if statement, would cout not found. So we'll do more examples. Maybe another example, go over also runtime analysis of these as well. But for right now, I'm going to go ahead and stop right there. We're almost out of time. So I guess take care, you guys. Stay safe. Thanks for watching. Have an awesome weekend. And I will see you guys next week.